The first example illustrates the basic steps to setting up a risk analysis for multiple hydrologically driven potential failure modes. The hydrologic hazard is represented by a stage frequency curve and is provided in tabular format. Relationships for the 5th percentile, 50th percentile, and 95th percentile annual exceedance probabilities are provided for each stage. To begin building the model, add a tabular hazard function by right-clicking on the Hazards folder in the Project Explorer window and selecting Add Tabular Hazard. RMC Total Risk also provides the user the option to pull in hazard data directly from other RMC-developed tools, such as BestFit and RFA. A word of caution, though. If you add straight from RFA, Total Risk tabulates the data from the RFA curves and then creates a PERT distribution for each stage. When running full uncertainty, the mean probabilities that result may or may not line up with the expected value from RFA. To check, run the analysis both deterministically and probabilistically. If the mean results do not match very well, it is recommended that a different distribution be assigned. How to run deterministic and probabilistic analyses will be covered later in this module. Name the hazard function in the prompt and click OK. Use the first drop-down to change the uncertain variable to probability, and the second drop-down to select PERT percentile Z as the distribution. In the Properties window, verify that the hazard type and units are correct, and select the interpolation transforms. For the stage frequency curve, the hazard type is stage, the units are given in feet, and we want to transform the probabilities to normal z-variate when interpolating, because the stage frequency curve is plotted on a probability scale. Next, copy and paste the hydrologic hazard table from the example file and paste it into the RMC total risk table. The software will plot the stage frequency inputs and the calculated mean. Next, because the risk analysis includes a potential failure mode that is a function of spillway discharge, PFM2, we need a transform to convert stage to spillway discharge. Right-click on the Transform folder and select Add Tabular Transform. A prompt will appear for you to name the tabular transform. Now that a deterministic table has been added, copy the stage to spillway discharge data from the example file and paste it into the table on the screen. Review the plot and verify that the transform properties in the Property window are correct. The hazard type should be stage with units of feet. The transformed hazard will be flow with the units of CFS. You can customize this plot and any plot in RMC Total Risk by right-clicking on either axis or in the middle of the plot area. For the interpolation transforms, choose none for the hazard to keep the stage linear, but change the transform hazard to logarithmic since we are dealing with discharge or outflow. We are also going to need a transform that moves from flow back to stage because the consequences given for PFM2 are a function of stage. Create a tabular transform just like we did prior, but with inputs reversed. X is now flow and value is now stage. The hazard type is flow in CFS and the transformed hazard is stage in feet. With the hazard and transform relationships built, it is time to add a system response by right-clicking on the System Response folder and selecting from the menu. The most common way will be to add an event tree response, but other options include parametric response, tabular response, and composites. Template event trees for many common failure modes have been preloaded into RMC Total Risk to speed up building a risk analysis. In the dialog box, type in the name of the PFM, select the hazard category, flood or seismic, and then choose a template. PFM1 in this example is backward erosion piping, so we will choose backward erosion piping from the drop-down list and click OK. The software will import the typical backward erosion piping event tree into the tab document window. To start inputting data into the event tree, first click on the fan symbol at the first node. This is where the hazard levels used to define the system response will be input. Copy the stages from the example file and paste them into the properties window to the right. Also, while we are over here, change probability transform to logarithmic so the software will perform semi-log interpolation when interpolating from the system response. Linear for stage, logarithmic for probability. Next, we copy the Node 1 triangular distribution data from the example file. Then click on Node 1 branch of the event tree. A system response table will be ready for input in the Properties window. Choose Triangular for the distribution and paste the Node 1 data into the table. Repeat the process for the second node as shown here, and then for all remaining nodes in the event tree. This one is a deterministic node. Once finished inputting the data for all nodes, click on Response to view the system response relationship. The mean system response is plotted along with the 90% confidence. Repeat this process to input the system responses for the other potential failure modes. Right-click on System Response to add an event tree system response. PFM2 is concrete line spillway erosion. And the event tree will look like this. Copy the spillway discharges that define the system response from the example file. Click on the fan icon next to spillway discharge at the beginning of the tree, then paste the values into the Properties window under the hazard levels. Be sure to change the hazard type to flow, the units to CFS, and both the hazard and probability to logarithmic for the hazard transform, because we are working with flow and system response probabilities. Copy the node data and paste the distribution data into each corresponding event tree branch. Once finished, the system response plot should look like this. Repeat the general process one last time to add an event tree for PFM3 overtopping. Choose the embankment overtopping erosion template and input the data from the example file like we've done before. As with the other failure modes, copy the stage data and paste it into the Properties window. Do the same for the node data to fill out the event tree. Because this is an overtopping failure mode, leave both interpolation transform inputs as none for linear interpolation. Once finished, the system response plot for PFM3 overtopping will look like this. The next step is to add in the consequences. Right-click on the Consequences folder and choose Tabular Consequence for this example. RMC Total Risk also allows the user to input consequence functions directly from LifeSim. We will need several consequence functions. The first is for the non-breach day life loss. Choose a PERT distribution from the drop-down at the top. Copy the non-breach day life loss data from the example file and paste it into the table in the Tab Documents window to get this plot. Now repeat for the non-breach night life loss. Copy and paste the non-breach night life loss data from the example file. You will have to do this one in 2 steps because the stage is not right next to the night life loss portion of the table like it was for the day. The plot of the non-breach night life loss is shown here. Next, we need to weight the life loss functions by their associated exposure probabilities using a composite function. Right-click on the Consequences folder and select Add Composite Consequence. Name it non-breach or something similar. In the Properties window, press the first icon with the green plus sign twice to add rows for 2 consequence functions. Select non-breach day for the first input and non-breach night for the second input. We are told to assume a 10-hour workday, so the day exposure is equal to 10 divided by 24, or 0.417, and the night exposure is equal to 14 divided by 24, or 0.583. Once the exposure weights have been input, the exposure weighted consequences will be plotted as shown. Repeat this process for the breach life loss associated with each potential failure mode. Here is the day life loss for PFM1. The night life loss for PFM1. And the exposure weighted life loss for PFM1. The same procedure is followed for the other PFMs as well. Here is the day life loss for PFM2. The night life loss for PFM2. And the exposure weighted life loss for PFM2. Finally, the day life loss for PFM3. The night life loss for PFM3. And the exposure weighted composite for PFM3. Now that we have inputs for all parts of the risk equation, it is time to build a risk analysis. Right-click on Risk Analysis and choose Add Risk Analysis. Click the plus sign in the top left and select Hazard to start building the risk diagram or project event tree. Use the drop-down to select Stage Frequency, then click on the yellow circle to add consequence and system response functions. The first connection to the hazard will be the non-breach consequences, so choose Add Consequence and choose Non-Breach from the drop-down. Next, add the PFM starting with PFM1. Click the same yellow circle as before and choose Response. Then select PFM1 from the drop-down menu. Add a consequence function for PFM1. And select PFM1 Breach. The process for PFM2 is a bit different because a transform is needed to go from stage to spillway discharge. Click on the yellow circle and choose Add Transform. Select Stage to spillway discharge, then build out the rest of the tree. Add the PFM2 response next, then another transform to convert discharge back to stage, and then to the consequences, which are a function of stage in this example. Add in the response and consequences for PFM3, and the risk diagram is complete. Before running the analysis, double-check the message window. We have no errors, but several warnings. These warnings are typical and are related to the hazard relationship starting at elevations lower than the lowest stage evaluated for the consequences. The stages are close enough to each other that these warnings can be ignored, but it's always best to define consequence and system response relationships for the full range of loading. Before running the analysis, let's check the properties options. Set the realizations to 10,000 to get a good estimate of the uncertainty. We were instructed in the example file to use the competing risk model, so choose that option from the failure mode method. Everything is ready to run. Click back on the General tab of the Properties window, select Simulation Risk with Full Uncertainty, and click Estimate. It should only take a minute or so for the analysis to complete. Many of the terms in our MZ total risk are different than the dam safety terms that we are used to. Under risk types, there are 5 options to choose from: incremental, background, total, failure, and non-failure. Incremental refers to the incremental risk for the project. Background refers to the non-breach risk. Total refers to the residual risk. Failure plots the annual probability of failure with the total breach consequences instead of the incremental, and non-failure is the complement of the failure with associated non-fail consequences. The loss exceedance curve is more commonly known as the Big FN chart and is shown here. Here is the non-breach or background loss exceedance curve and the curve for the total or residual risk. The FN plot for the example, titled Alpha Eta in the software, is shown here. We were only given life loss consequence data, but had we been given economic cost data and wanted to calculate the economic risk, the changes would be to swap out the life loss functions for the economic cost functions in the risk diagram and run a separate risk analysis. You can also view a summary table of the results to see the total risk. You can also pull in the marginal risk associated with each potential failure mode by clicking on Risk Analyses and Failure Modes. On the Alpha Eta tab, you can plot the marginal risk of the PFMs along with the total by following a similar procedure. That plot is shown here. From the Diagnostics tab, you can view a variety of helpful plots and pull out the tabular output data from a risk analysis after it was run. This completes example 6.1.